Hello everyone, this video is for visually impaired students. Let's start organosulfur compounds. Introduction. Sulfur is placed in the third period of the periodic table just below oxygen in group 16. During the recent past, a lot of work has been carried out in the area of organosulfur compounds, primarily due to their importance in industry, pharmaceuticals and metabolic processes. Therefore, in this unit, we shall discuss some important aspects of the chemistry of organosulfur compounds. Structural features. Both oxygen and sulfur after the chemical nature of carbon atom to which they are attached, but unlike oxygen analogues, in most of sulfur compounds, the reaction occurs by the attack of a nucleophile, an electrophile, or even a free radical at the sulfur atom. Another marked difference between oxygen and sulfur compounds is that unlike oxygen, which readily forms double bonds, sulfur is reluctant to form double bonds by pp overlapping. Thus, when the exception of carbon disulfide, thiocancel compounds are quite unstable and readily undergo addition reactions. In other words, thioaldehydes and most of thioketones can be generated only as transient intermediates that rapidly undergo dimerization, trimerization, polymerization to form compounds having only sigma bonds. For example, the instability of the thiocarbonyl compounds is primarily due to the difference in the size of the 2p orbital of carbon and 3p orbital of sulfur, which makes 2p 3p overlapping relatively ineffective. In addition to poor 2p 3p overlapping, sulfur is also reluctant to form 3p 3p pi bonds with other sulfur atoms. It is because of this reason that elemental sulfur does not exist as diatomic S2 molecules. Instead, it prefers to form only SS sigma bonds and exist as a nonpolar octatomic molecule S8 having crown shape as shown in figure. Further, due to large size of sulfur atom, SS bond is quite long. As a result, the two 3p orbitals, one on each S atom, cannot come close enough to undergo 3p 3p overlap to a significant extent. Hence, the pi bond between 3p 3p orbital is very weak. It may, however, be noted that unlike thioaldehydes and thioketones, thioamides and thioacids are isolable and hence are relatively stable. The contradicts the generalization that pi bonds involving sulfur atoms are very weak. The actual reason for their stability is the resonance stabilization involving lone pairs of electrons on nitrogen of oxygen atom. Here, the contribution of structure 2 towards resonance hybrid of thioamides and that of structure towards resonance hybrid of thioacids is significant because both of them have only single bonds between C and S atoms. We have discussed above that sulfur has little tendency to form pi bonds through pp overlap. However, many sulfur compounds such as dimethyl sulfoxide, a widely used protic solvent, have pi bonds between sulfur and oxygen atoms. And anticipated, the double bond, like any other double bond, consists of a pi bond and a sigma bond. The pi bond is formed by head-on overlap between an sp3 orbital of sulfur and one of the half-filled p orbitals of oxygen. The other two sp3 orbitals of S overlap with sp3 orbitals of two alkyl groups to form two additional sigma bonds, while the fourth sp3 orbital contains a lone pair of electrons. Sulfur is now left with a half-filled d orbital, and oxygen also has an half-filled p orbital. Since dxy lies in the plane of 2py orbitals, hence dzx lies in the plane of 2pz orbital. Therefore, d pi p pi overlap occurs either between dxy and 2py orbitals to form a pi bond. In valence bond terms, this d pi p pi bonding implies that DMSO may be regarded as a resonance hybrid of the following contributing structures. Since DMSO has a high dipole moment, this suggests that structure 1 makes a significant contribution towards the resonance hybrid, which of course is much greater than that of structure 3. An important difference between extraordinary double bonds with p-pi p-pi overlap and sulfur oxygen double bonds with p-pi d-pi overlap is that groups attached to sulfur do not lie in a plane. This explains why acetone is planar while DMSO is non-polar. Structure of thiols and thioethers. Both in thiols and thioethers, S is sp3 hybridized in the ground state. Such a sp3 hybridized sulfur has two half-filled orbitals which overlap with a sp3 orbital of an alkyl group and a s orbital of the H atom, as in thiols, or with sp3 orbitals of two alkyl groups as in thioethers. Each of the remaining two sp3 orbitals contain a pair of electrons. However, due to greater lone pair repulsions than bond pair repulsions, the CSH bond angle decreases from 109 degree 28 minutes to 100 degree in CS3SH. In contrast, in thioethers, due to greater steric hindrance between two alkyl groups than between an alkyl group and a hydrogen atom in thiols, the bond angle in thioethers is larger than in thiols. For example, methyl thioether has a bond angle of 105 degree. Structure of sulfonic acid. In sulfonic acids, S is sp3 hybridized. Since here we need to form two sulfur oxygen double bonds. Therefore, both the 3s and 3p electrons are promoted to d orbitals as shown below. The four sp3 orbitals of sulfur form four sigma bonds, one with the carbon atom of the alkyl or aldehyde group, three with O atoms, and S is now left with two unhybridized d orbitals which overlap with p orbitals of two oxygen atoms to form two d pi p pi s double bond O bonds. The p orbital of the third oxygen atom overlaps with s orbital of hydrogen to form an OH bond. Nomenclature. For the purpose of nomenclature, sulfur compounds are classified according to the valence state of sulfur. The compounds containing bivalent sulfur are structurally analogous to the corresponding oxygen compounds such as alcohols, carbonyl compounds, carboxylic acids, etc. Therefore, they are often named by adding the prefix thio to the name of corresponding oxygen analog. For example, thioalcohol, thiophenol. Thiols or thioalcohols, just as alcohols are alkyl derivatives of H2, in the same way thioalcohols are alkyl derivatives of H2S. Thus, the general formula of thioalcohols is RSH. In the IUPAC system, thioalcohols are called thiols. They are also called mercaptans since they react with mercury ions to form insoluble mercury compounds. The functional group of thioalcohols is SH, which is called sulfyl dryl thiol or mercapto. A number of sulfur compounds are found in nature. For example, butan thiol is found in skunk, an American animal. Propane thiol occurs in onions. Allyl mercaptan and allyl disulfide occurs in garlic. Nomenclature of thiols. Common name. In the common system, thioalcohols are called mercaptans. The individual name of any thioalcohol is then derived by adding the word mercaptan of the name of the alkyl group. IUPAC name. In the IUPAC system, thioalcohols are called thiols. The individual name of any thioalcohol is then obtained by adding the suffix thiol to the name of the hydrocarbon containing the same number of carbon atoms. In case of isomeric thiols, the position of the SH group is indicated by the lowest possible Arabic numerical. The common and IUPAC names of some special thiols is given below. In case of polyfunctional compounds, the thiol is named as mercapto, derivative of the principal functional group. It may be noted that OH group is assigned higher priority both in numbering and naming. Methods of formation. Thioalcohols are generally prepared by the following methods. From alkyl halides. When alkyl halides are heated with a large excess of sodium or potassium hydrosulfide, thiols are formed. From sodium alkyl sulfate or para-toluene sulfonic ester. When sodium alkyl sulfate is heated with sodium hydrogen sulfide, thiol is formed. From alcohols, mercaptans are prepared from alcohols either by treating with phosphorus pentasulfide or by passing a mixture of hydrogen sulfide and alcohol vapors over thoria catalyst at 73 Kelvin. From alkenes, addition of hydrogen sulfide to the carbon-carbon double bond of an alkene in presence of nickel sulfide as catalyst leads to the formation of thiols. The addition occurs in accordance with Markovnikov's rule. Terminal thiols can, however, be prepared by free radical addition of H2S to an alkene. From thiourea or S-alkyl thiouronium salts. When alkyl bromides or iodides are treated with thiourea, S-alkyl so thiouronium salts are produced. These upon alkaline hydrolysis give thiols in about 80 to 90% yield. This is best method for preparing thiols. From Grignard reagent. The reaction of Grignard reagent with sulfur powder gives addition products which upon hydrolysis gives thiols. Physical properties. Physical state. Smell. Methane thiol is a gas while other thiols are colorless volatile liquids with disagreeable smells. The lower membrane have extremely strong smell while other higher members have mild odor. The odor of freshly cut onions is due to propane 1 thiol. That of garlic is partly due to propane 2-in-1-thiol. Small quantities of ethane thiol are added to LPG to warn against leakage of the gas. Bonding points. Due to absence of H bonding, the boiling points of lower thiol alcohols have lower than those of corresponding alcohols. However, thiols having 8 or more carbon atoms have slightly higher boiling points than corresponding alcohols due to stronger van der Waals forces of attraction and weaker H bond solubility. Thiols are less soluble in water than the corresponding alcohols. This is due to the reason that thiols cannot form H bonds with water. Dipole moment. Due to small electronegativity of S than O, SH bond is less polar than OH bond. As a result, thioalcohols have lower dipole moments than their corresponding alcohols. Chemical reaction. The thiols resemble alcohol in many ways. The main difference in their behavior is towards oxidizing agents. Some important chemical reactions of diols are discussed below. Acidic nature. Thioalcohols are stronger acid than alcohols. This is because of the following two reasons. The bond dissociation energy of SH bond is much lower than that of OH bond. As a result, SH bond is cleaved more easily than OH bond. An ion left after the removal of a proton from RSH, that is RS negative, has negative charge on S atom, while in case of alcohol, RO negative, it is an oxygen atom. Because of the larger size of sulfur, RS negative can accommodate the negative charge more easily than the smaller oxygen atom in RO negative ion. Some important reactions of thiols due to their acidic nature are discussed below. Reaction with alkalis. Due to their stronger acidic nature, they dissolve in NaOH and KOH, forming their corresponding salts called merceptides. The reaction is reversible and the merceptides are completely hydrolyzed by water in absence of alkali. Reaction with the mercury oxide. Being acidic, thiols react with mercuric oxides to form mercury merceptide. Action of alkali metals. Alkali metals being strong base react with mercaptans to form the corresponding mercaptines with evolution of H2 gas. Action of heavy metals. When a thiol is treated with the aqueous solution of the salt of a heavy metal, example lead acetate, a merceptide bond is formed. Reaction of carboxylic acids. Thiols react with carboxylic acids, preferably in presence of an inorganic acid as catalyst, to form the corresponding thioesters. The equilibrium lies mainly to the left. However, a good yield of an ester is obtained if acid chloride is used instead of acid. Oxidation. Due to weaker SH bond, thiols can be easily oxidized. The nature of the product, however, depends upon the nature of the oxidizing agent used. With mild oxidizing agents such as air, H2O2, CuCl2, or sodium hypochlorite, thiols are oxidized to dialkyl sulfides. An alkaline solution of sodium plumbite containing sulfur also converts thiols to dialkyl sulfides. Dialkyl disulfides can also be prepared by the action of iodide on sodium merceptides. With strong oxidizing agents such as HNO3, periodic acid, etc., thiols are converted into sulfonic acids. This gives us an important point of difference between thiols and alcohols in their behavior towards oxidation. Whereas in alcohols, oxidation occurs the oxidation state of carbon, while in case of thiols, the oxidation state of sulfur increases. For reduction, on treatment with Raney nickel, thiols readily undergoes desulfurization to form the corresponding hydrocarbons. Action of aldehydes and ketones. Thiols readily combine with aldehydes and ketones in presence of hydrochloric acid to form mercaptals and mercaptols respectively. For example, when these mercaptals and mercaptols in ethanol are refluxed in the presence of Raney nickel, the thiol group is replaced by hydrogen. Thus, mercaptal formation of inacidic medium followed by disulfurization with Raney nickel gives us an excellent method for conversion of a carbonyl group to methylene group under neutral conditions. This method is, however, competitive with Clemmensen reduction, which is carried out under acidic condition, with Wolff-Kishner reduction, which is carried out under basic conditions. Further, these mercaptals and mercaptols on treatment with mercuric chloride in presence of cadmium carbonate regenerate the original aldehyde ketone. Therefore, like acetyl ketones, mercaptals and mercaptols can also be used for protection of the aldehyde ketones group in the acidic medium. Oxidation of mercaptals. Mercaptals are easily oxidized to sulfonols. For example, oxidation of acetone mercaptol with KMnO4 gives sulfonol. Thioethers may be regarded either as dialkyl derivatives of H2S or alkyl derivatives of thioalcohols. They may also be regarded as derivative of ethers in which oxygen has been replaced by sulfur. The common name of thioethers are obtained by adding the word sulfide or thioether to the names of the alkyl group arranged in alphabetical order. In the IUPAC system, thioethers are named as alkyl thioalkanes. The sulfur atom is taken with the smaller alkyl group which forms a part of the alkyl thio group. The larger alkyl group forms a part of the alkane. Methods of formation. Number 1. By heating potassium sulfide with an alkyl halide, potassium alkyl sulfate or potassium thiosilate. By heating an ether with potassium pentasulfide. Number 3. By heating an alkyl halide with sodium mercaptide. This method is similar to Williamson synthesis, can be used for synthesis of both symmetrical and symmetrical thioethers. Since alkyl sulfide is a better nucleophile than alkoxide ion, the reaction is very rapid and gives excellent yields. 4. By addition of a thiol to an alkane in presence of peroxides. 5. By passing a thiol over a mixture of heated alumina and zinc sulfate at 573 Kelvin. Physical properties. Physical state. Thioethers are colorless, oily liquids having unpleasant smell. Solubility. They are insoluble in water but soluble in organic solvents such as alcohols, ethers, etc. 3. Boiling points. In general, their boiling points are relatively higher than those of corresponding ethers. This is due to stronger van der Waals force of attraction in thioethers as compared to ethers, primarily due to the bigger size of sulfur than oxygen atom. Chemical reactions. Although ethers are relatively unreactive, thioethers are reactive. The reactivity is primarily due to the ability of the divalent sulfur atom to get converted into compounds with 4 and 6 oxidation state. The main difference lies in the formation of sulfoxides and sulfones on oxidation and to form sulfonium salts with alkyl halides. Some of their important chemical reactions are described below. Weak basic character. Due to presence of lone pair of electrons on the S atom, thioethers like ethers behaves as weak base. As such, they dissolve in 100% H2SO4 to form sulfonium salts. 2. Reaction with alkyl halides. Being sufficiently nucleophilic, thioethers react with alkyl halides by a central mechanism to form trialkyl sulfonium salts. A noteworthy feature of sulfonium salts is that they are tetrahedral, the orbital containing the lone pair of electrons being considered as the 4th substituent. If the 3 substituents attached to the sulfur atoms are different, sulfonium salts behave as chiral molecules have been resolved into stable enantiomers. It may be noted here, tertiary amines of the type R1, R2, R3N could not be resolved in spite of the fact that they have tetrahedral structure. The reason cited was that of the energy difference between the two enantiomers was low and the rapid interconversions between the two enantiomers gave a racemic mixture. However, in case of sulfonium salts, the energy difference between the two enantiomers is sufficient high, hence cannot be readily interconverted. Hence, sulfonic salts can be easily resolved. These sulfonium salts are stable at room temperature but decompose on heating to alkyl sulfide, alkyl halide. With the most moist silver oxide, these sulfonium salts form sulfonium hydroxide, which is a strong base. These sulfonium hydroxide decompose on heating to form the original alkyl sulfide and an alkene. This reaction may occur either by E2 or E1 mechanism depending upon the nature of the alkyl groups. If all the groups are 1 degree, the reaction occurs by E2 mechanism. If, however, one of the group is 3 degree, the reaction occurs by E1 mechanism. 3. Formation of sulfur halides and their reaction. The sulfonium salts on treatment with a strong base such as N-butyl lithium eliminate an alpha hydrogen to form dialkyl sulfonium methylides, commonly known as sulfur halides. These sulfur halides are extremely useful synthetic reagents and have been widely used for the synthesis of epoxides and cyclopropene derivatives by reacting them with a ketone or an activated olefin as shown below. 4. Oxidation. Thioethers on oxidation first give sulfoxides and then sulfones. With mild oxidizing agent like HiO4 at 273 Kelvin, oxidation can be stopped at the sulfoxide stage. With moderate and strong oxidizing agents, such as H2O2 in glacial acetic acid, diethyl sulfide gives first diethyl sulfoxide and then diethyl sulfones. Reduction. Alkyl sulfides, on treatment with uranium nickel, readily undergo reduction in disulfurization, forming alkanes. Reaction with bromine. Alkyl sulfides form many additional products. For example, the addition of bromine gives dialkyl sulfide dibromide. Sulfonic acid. Sulfonic acids are generally organic compounds having general formula RSO3H, where R may be an alkyl or aryl group. The aliphatic sulfonic acids are named either as alkyl sulfonic acids or as alkane sulfonic acids, while aromatic sulfonic acids are named only as arene sulfonic acids, for example, methyl sulfonic acid or methane sulfonic acid. Methods of formation. Aliphatic sulfonic acids. These are generally prepared by following methods. Oxidation of thiols. Thiols on oxidation with HNO3, KMNO4, NaOBr, etc. undergo oxidative coupling to form the first dialkyl disulfides, which under the condition of the reaction are further oxidized to alkyl sulfonic acids via thiosulfate ester. 3. Sulfonation of alkanes. Sulfonation of alkanes with concentrated H2SO4, oleum or chlorosulfonic acids give alkane sulfonic acids. The sulfonic acids group generally enters the chain at second carbon atom. Action of sulfuryl chlorides on alkanes. The action of sulfuryl chlorides, or a mixture of Cl2 and SO2 on an alkane in presence of light or peroxide at 313 to 323 Kelvin gives the corresponding alkane sulfonyl chloride in high yield. Here again the SO2Cl group enters mainly at the second position of the chain through a varying amounts of product with this group at the first carbon are also formed. 4. Strecker reactions. Sodium salts of sulfonic acids are obtained when an alkyl halide is heated with sodium sulfide. 5. Addition of sodium bisulfite to alkanes. In presence of oxygen or peroxides, antimargonic addition of sodium bisulfite to alkanes give the sodium salt of the corresponding alkane sulfonic acid. For example, sulfonamides are derivatives of sulfonic acid in which OH part of the sulfonic acid group has been replaced by NH2 group or on the substituted amino group such as NHR and R2. For example, preparation. Sulfonamides are generally prepared by the action of ammonia, primary secondary amines on the corresponding sulfonyl chlorides, for example, benzene sulfonyl chloride, methylamine. Properties. Sulfonyl amides are well-defined crystalline solids and are therefore used to characterize sulfonic acids. Acidic nature. They are weakly acid in nature and hence react with strong alkalis to form water-soluble salts. Hydrolysis. Sulfonamides on heating with aqueous acids or alkalis undergo hydrolysis to form the corresponding sulfonic acids. Uses. They are used in the manufacture of dyes, antiseptics such as chloramine T and sulfur drugs. Synthesis. Acetanilide on chlorosulfonation with excess of chlorosulfonic acid gives para-acetamidobenzene sulfonyl chloride, which upon treatment with guanidine followed by acid hydrolysis give sulfaguanidine. Guanidine needed for the purpose that it itself prepared by heating cyanamide with ammonium chloride. Uses. Sulfaguanidine is an important sulfur drug and used for treatment of bacillary denatry since it is only slightly absorbed in the intestinal tract. Therefore, it is given in a relatively larger doses. Synthetic detergents. These days, in place of soap, substances which are being largely used as cleansing agent are synthetic detergents. As the name suggests, they are obtained from purely synthetic chemical as compared to soaps which are derived from chemical obtained from natural sources like oil, fats. In fact, synthetic detergents are sodium or potassium salts of long chain alkyl hydrogen sulfates or aryl sulfonic acids. Unlike soaps, synthetic detergents can also be conventionally used even in hot water. This is due to the reason that calcium, magnesium salts or detergents like their sodium potassium salts are also soluble in water. Hence, synthetic detergents do not form curdy white precipitates with hot waters. Further, they can also be used in acidic solution. However, synthetic detergents have one disadvantage. Unlike soaps, they are not completely biodegradable and hence cause water pollution. The typical synthetic detergents are either alkyl sulfates or alkyl benzene sulfonates. Sodium alkyl sulfonates. These are obtained from long chain alcohols by treatment with concentrated H2SO4 followed by neutralization with NaOH. Some important examples of this type of detergents are sodium lauryl sulfate. These sodium alkyl sulfates are 100% biodegradable. These are also effective in slightly acidic solutions since they form an alkyl hydrogen sulfate, which is a soluble material, whereas soaps reacts with acidic solutions to form insoluble fatty acids. B. Alkyl benzene sulfonates. The most commonly used domestic detergents these days are linear alkyl benzene sulfonates such as sodium benzene sulfonate. These are anionic detergents and are obtained by conversion of benzene into long chain alkyl benzenes followed by sulfonation and neutralization with NaOH. Another important example of sodium P is it is prepared by Friedel-Crafts alkylation of benzene with a long chain alkyl halide or an alkene or an alcohol followed by sulfonation and neutralization with NaOH. Alkyl benzene sulfonates in which the phenyl group is either attached at the end of the long alkyl chain or any other secondary position have high biodegradability, hence are called soft detergents, while alkyl benzene sulfonates having branched chain alkyl group have poor biodegradability, hence are called hard detergents. Cleansing action of soap and detergents. All the soap and detergents contain two characteristic groups, a water soluble and an oil soluble. As a result, one end of the molecule um, tends to go into the oil phase and other tends to go into the water phase, with the net results that material concentrates at the surface of the solution or interface. The dirt is generally held in a dirty surface by a thin film of an oil or grease. When the dirty surface is treated with soap solution, the non-polar hydrocarbon chain of the soap or detergent dissolves in oil or grease, and the carboxylate group of the soap and the sulfonate group of the synthetic detergents is held by surrounding water. This lowers the surface tension between water and grease. As a result, a stable emulsion of oil in water is formed when the surface on the cloth is mechanically scrubbed. The loosened dirt particles are absorbed by colloidal soap or detergent particles and ultimately washed away. Thanks.